Hello everyone. In this video, we shall continue discussing the succeeding cases of hypothesis testing for the two population means. In the previous video, we have discussed the idea or concept of hypothesis test for the two population parameters, and we have discussed already the first case of hypothesis test for the two population means. Now, in this video, we shall discuss the second case, which also involves independent samples, but we're going to use the option about the pooled variance t-test. So again, to recall, samples are said to be independent of each other if the data obtained from one sample is independent of the data obtained from the other sample and vice versa. So for instance, if we are comparing the average grades of students from traditional classes and the average grades of students from classes under online methods, we get samples or data from the first group and samples or data from the second group. Now, the grades that we get from students in the traditional classes do not affect the grades of the students under the classes under online methods. So here we say that these two sample groups or the sample data that we get from these two sample groups are independent of each other. Now, the second case about the hypothesis testing for the two population means is the pooled variance t-test. In here, we assume that the samples or the independent samples are taken from normal populations. So which means that the values from the first population group is normally distributed, and the values from the second population group are also normally distributed. Now, in this case, the population standard deviation of the first and the second group are unknown, but they are assumed to be equal. So which means that the widths of the normal curves from the two populations are the same. Now, in this case, we also require that our sample sizes are both less than 30. Now, this case uses the t-distribution, which you already encountered in the previous lessons in statistics. Now, the formula for the test statistic for this case number 2 is t is equal to the sample mean of the first group minus the sample mean of the second group minus the hypothesized difference d sub 0 divided by the square root of the pooled variance sp squared multiplied by the quantity of 1 over the sample size of the first group plus 1 over the sample size of the second sample group. Now, the pooled variance can be computed using the following formula. The formula for the pooled variance is sample size of the first group minus 1 multiplied by the standard deviation of the first group square plus sample size minus of the second sample group minus 1 multiplied by the sample standard deviation of the second group square divided by the total of the two sample sizes minus 2. Now observe here that the total of the two sample sizes minus 2 is our degrees of freedom, which is a parameter of our t-distribution. So we shall use this degrees of freedom in order to get the critical values later in our hypothesis test. So to illustrate this particular case, let's consider this example. A study was made to determine if the subject matter in a physics course is better understood when a lab constitutes part of the course. Students were allowed to choose between a 3-semester hour course without labs and a 4-semester hour course with labs. In the section with labs, 11 students made an average grade of 85, with a standard deviation of 4.7. And in the section without labs, 17 students made an average grade of 79 with a standard deviation of 6.1. Now, would you say that the laboratory course increases the average grade? Use a 0.05 level of significance and assume that the populations to be approximately normally distributed with equal variances or equal standard deviations. And let us analyze why this problem falls under the second case or the pooled variance t-test. So it is assumed that the samples are independent from each other. So in this case, our first sample group is that we get the students with labs, and then the second sample group would be the students in the courses without labs. We are comparing here the average grade of those students with lab and the average grades of those students without laboratory. Now, we get samples from each of these population groups. Now, it is assumed that the data obtained from the two population groups are both normally distributed. So, which means that the values from the first population group follows this normal distribution, and the values from the second population group also follows a normal distribution. And it says here that the variances or the standard deviations of these normal distributions are equal. So which means that the normal curves here have the same width. Or we say that the standard deviation of the first population and the standard deviation of the second populations are equal. Now also, the sample sizes obtained from these two populations are 11 and 17 respectively. So which means that n sub 1 equals 11 and n sub 2 is equal to 17. So since all the requirements for case 2 are satisfied, this example falls under the pooled variance t-test. Now, according to the given information, the average grades of the 11 students is 85, while their standard deviation is 4.7, while the average grades of the 17 students without lab is 79, and the standard deviation is 6.1. So to test our hypothesis, the claim in this problem states that the lab course increases the average grade. So which means that the average grade from the classes with labs is higher than the average grade from the classes without labs. And since we're using the strict greater than symbol here, we put this in our alternative hypothesis. And our null hypothesis would be the complement of this, which is mu sub 1 is less than or equal to mu sub 2. Now, of course, if we transpose mu sub 2 to the other side, it's going to be mu sub 1 minus mu sub 2 is greater than 0, which indicates that our hypothesized difference is 0. So this slide here shows step number 1. So since our alternative hypothesis uses the strict greater than symbol, the type of test would be a right tail test, or we call it an upper tail test. Now, since this problem is under case 2, we're going to use the t-distribution. So since our level of significance is 0.05, we shade the rightmost part of the t-distribution, and the area to its right side is 0.05 or 0.0500. So this is our rejection region, and the boundary of this rejection region and the non-rejection region would be our critical value. So this critical value will be obtained from the t-distribution table, which also makes use of the degrees of freedom. So the degrees of freedom formula for the pooled variance t-test is n sub 1 plus n sub 2 minus 2. So in this case, it's going to be 11 plus 17 minus 2, which is 26. So we shall use 0.05 and this degrees of freedom equal to 26 in order for us to read the critical value. So in this t-distribution table, we find 0.05 and degrees of freedom 26. And then we get the intersection of those two. So we get 1.7056. So that means that the critical value is 1.7056. So which means that our critical region would be to reject the null hypothesis if the t-test statistic is greater than 1.7056. So in order to determine if our null hypothesis is rejected or not, we shall compute first our test statistic. So for case number 2 or the pooled variance t-test, we have to compute first for the pooled variance SP squared. And we just plug in the necessary values that we got from our samples. So in our numerator, we have 10 times 4.7 squared. This is from 11 minus 1. And then this one is from 17 minus 1. So that's 16 times 6.1 squared divided by our degrees of freedom, which is 26. So this tells us that our pooled variance is 31.39. So we shall use this pooled variance in the formula of the t-test statistic. And then if we plug in the necessary values, we get 2.77. So recall that the sample mean of the first group is 85. The sample mean of the second group is 79. And our hypothesized difference is 0. So since 2.77 is our t-test statistic, 2.77 is somewhere to the right side of 1.7056. So which means that 2.77 is indeed greater than 1.7056, which means that our decision is to reject our null hypothesis. So going back to our step number 1, since HO is rejected, we put an X mark in our HO and a check mark in our alternative hypothesis. And since the check mark and the claim belongs to the same hypothesis, this means that there is sufficient evidence to say that the average grade of the students in the section with labs is higher than the average grade of the students in the section without laboratory. So which means that we have sufficient evidence to say that the lab course increases the average grade. So let us use the PHStat software in computing the test statistics. So let's copy this problem first into our Excel file. So let's suppose that we were using the same problem again. Okay, so in the add-ins portion or options, we click PHStat. And then since we have the sample means and the sample standard deviations already, we shall use the summarize data option. And then we pick the pooled variance t-test. Okay, so in the hypothesized difference, we will put 0. And from the problem, it says that the level of significance is indeed 0.05. Now, our first population involves the data coming from the section with labs, and our sample size is 11. Sample mean is 85. sample standard deviation is 4.7. And then for our second group, for the section without labs, we got 17 students, and the average is 79, and the sample standard deviation is 6.1. Now, since our type of test is right tail test, we click upper tail test here, and then we click OK, and then we get the following PH step output. So as you can see here, that our t-test statistic is 2.7674 or 2.77, and our critical value is 1.7056. So since the critical region is to reject HO if the t-test statistic is higher than the upper critical value, then we reject the null hypothesis. So this ends the video about case number 2 of hypothesis testing for the two population groups. Thank you for listening.